Okay, in this video we're going to talk about a couple of topics that relate to proteins, specifically the Henderson-Hasselbalch equation, isoelectric point, and electrophoresis. All right, so one thing about proteins and amino acids is that they can exist in a couple of different forms depending on what the pH of the solution that they're in is. So going back to what we talked about when we were doing the doing weak acids and weak bases, if you look at the structures of the amino acids, all right, one thing that you might recognize about them is that they can both be a weak acid and a weak base. All right, so what I mean by that is one thing that they all contain is this amine right here, and amines have the ability to be a weak base. All right, remember that there's a lone pair of electrons on that nitrogen, and it has the ability to accept an H plus from solution. So this part of the molecule means that it has the ability to act as a weak base. All right, there's also this carboxylic acid part of the molecule, and that has the ability to donate an electron. So that part of it means that it has the ability to be a weak acid. Okay, and recall that whenever you have weak acids and weak bases, you have an ability for something to exist either as its acid or conjugate base form. All right, and another way that we talked about that was either the HA form or the A minus form. All right, so the interesting thing is that the structures that are shown in this in the data booklet are actually structures that you would never really see. All right, and what we're going to do is talk about why that is. So what we're going to do is talk about the nature of an amino group and a carboxylic acid group. So, as I said earlier, an amino group has the ability to accept an H+. All right, so doing this from right to left, if this thing accepts an H+, that would make this what you would call a protonated form, or the ammonium form of the amine. All right, and the reason that I drew it like this is so that we could then have an HA form of a, essentially this would be an acid. So if this is a base, that would make this the conjugate acid of that base. But another way to think about this is to say that this right here could be an acid, would be a weak acid, and that this, the free amine, would be the conjugate base of that acid. All right, so by comparison, remember, HA and A minus are all relative. All right, so remember, HA has got one more hydrogen than the A minus. All right, and notice that's true. All right, and also notice that the charge on HA is one greater than the charge on A minus. All right, and that is also true. This is a +1 charge. That is a neutral charge. So by comparison, it would fit that. All right, remember, HA does not necessarily mean that it has to be completely neutral. It's all just relative. All right, so if I write it this way, that's written as the standard acid dissociation. One thing that hopefully you recall is that there's this thing called a Ka. All right, and a Ka is the acid dissociation constant, and that essentially is a measure of how easily the acid will release one of that H+. All right, or how easily it will donate that H+. All right, so even though we can talk about it in terms of Ka, all right, and recall this is the way that the Ka expression is given, we could also talk about the pKa, and the pKa is the negative logarithm of the Ka. All right, and so essentially what another thing about Ka is, so one thing that a Ka allows us to do is to get a sense of which version of this would exist if we had it in solution. All right, and so if we had, so for an amine, or for an ammonium compound like this, the pKa is about 9.9. All right, so to get a sense of what that means, if we had this material, this amino acid in a solution, and we adjusted the pH of that solution so that it was greater than 9.9. All right, so we would do that by adding something like sodium hydroxide. All right, if that were to happen, then the predominant form that you would have would be this one right here. All right, but if we adjusted the pH of that solution so that the pH was less than 9.9, all right, the predominant material that you would have in solution would be this right here, all right? Okay, so we can do the same type of thing with the carboxylic acid. And remember, when I say R here, R has to be some sort of alkyl group, all right? R cannot be a carbon double bonded to an oxygen, all right? Same thing goes over here, all right? If it were to be like that, this pK would not be the same as what I'm reporting here, okay? But again, I'm just taking this carboxylic acid and I'm letting it act as an acid, all right? So if it does that, it donates its hydrogen, all right? So the pKa of this particular process is 2.2, or roughly about 2.2, all right? So again, what that means is that if the pH, if we had the amino acid, all right, which has this carboxylic acid group, and we had it in a solution where the pH was greater than 2.2, then what that means is that the deprotonated form, or what you would say the carboxylate form, would be the predominant form. All right. If we had a pH lower than 2.2, this would be the predominant form. All right. And so in terms of one other thing I want to remind you of, if the pH happened to be exactly 2.2, at that point you would have a 50-50 mixture of your A- and your HA form. All right. The higher the pH gets, the more of this you would have, all right? So, for example, if the pH was 3.2, which is 1 unit higher, you would have a 10-to-1 ratio of this to this. If it was 4.2, which is 2 units higher, you would have 100-to-1 of this species versus this species right here. So, the ratios that I just told you about when we give you a given pH and a pKa, and we talk about like what's the ratio of this particular version versus this particular version, can be given by what's called the Henderson-Hasselbalch equation. All right, so all the Henderson-Hasselbalch equation is a rearrangement of the standard Ka expression. All right, so here's the standard Ka expression, and again, you can use this for any particular acid-base acid dissociation equation. All right, so one thing that we can do with this is we could take the logarithm of both sides of this. All right, so we would have the logarithm of the Ka and the logarithm of this expression right here. All right, and one thing that our logarithm rules allow us to do, if we just focus on this side right here, is we could break up this side right here and express that as the logarithm of H plus the logarithm of A minus over top of HA. All right, and what that part is right there is a ratio of your A minus form, which would be the form on your right, to your HA form, which would be the form on the left of that. All right, so we can then, so recognizing that the pKa is the negative log of the Ka, the log of the Ka is the exact same thing as the negative pKa. All right, so same thing here. Remember that pH is the negative log of the hydrogen ion concentration. So log of the H plus would be the negative pH. So all we've done in going from this equation here to this equation right here is just turn this into the negative pH and turn that into the negative pKa. All right, so that gives us this expression right here. And if we take the pH and put it on the left and the pKa and put it on the right, it would give us these things as positive values rather than negative values. All right, so this expression right here, I know that's a little fuzzy, but that would be the log of the A minus over the HA. That is what's considered the Henderson-Hasselbalch equation. All right, it's written right there, and it's a pretty useful equation when you're talking about things like proteins, because whenever you have proteins, you have things that can be either have a hydrogen or not have a hydrogen at different pHs. All right, and this lets us figure out which form we would have. All right, so remember that the pKa is a property of your whatever weak acid you have. For example, for this carboxylic acid, its pKa is always going to be around 2.2. All right, you can adjust the pH of the solution that it's in by adding either a strong acid or a strong base. All right, so if we put this number in right here, and we just say, all right, well, at this given pH, what would the ratio of this to this? All right, so if you just put those numbers in and then you just solve for that ratio, it would tell you how much you have of each. All right. So one important rule of thumb that you can use without even using this equation is that for every unit higher the pH is than the pKa, that's a factor of 10 that you get of one thing versus the other. All right, so for example, if the pH is 3.2, that means you have a 10-to-1 ratio of this versus that. All right, if the pH is exactly 2.2, you have a 1-to-1 ratio. If you go 1 unit lower, if the pH was 1.2, you would have 10 of this for every 1 of this. All right, if it was 4.2, all right, so that's 2 units higher than the pKa, then you would have 100 of this for every 1 of this. All right, so and you could prove that to yourself by plugging the numbers into this equation right here. But let's move on to talking about how this is going to be applied to actual amino acids. So again, in the beginning of this video, I mentioned that the way that the structures of these amino acids are drawn in your data booklet would never be the actual structure that you would see for them. All right, and we can explain that with what we just talked about. Okay, so recall that all amino acids have both an amine, an NH2, and a carboxylic acid group. All right, so the first thing that we want to do is figure out, well, for that amine, all right, so for the NH2 part, would it exist like this, or would it exist with a hydrogen attached to it, that NH3 with the plus? All right, so taking a look at what we know about amines, all right, well, what we said here is that if the pH of the solution was less than 9.9, it would exist as this form right here. So if we had an actual amino acid, the amine at pH 1, all right, so if it's fairly acidic, would exist like this. All right, so what about the carboxylic acid? Well, we said that if the pH was greater, all right, so if we said that the pH was less than 2.2, it would exist like this. All right, so at pH 1, the carboxylic acid would exist as the HA form. All right, so both of these are existing. Both the amine and the carboxylic acid are existing at their HA forms at that particular pH. All right, let's go to the other extreme. Let's go to a really high pH. All right, well, at pH is higher than 9.9, the amine is going to exist as what you would say it's free amine, which is the A- form. All right, and anything above 2.2 is going to exist as the carboxylate. All right, so at pH of 12, all right, this would be the form of the carboxylic acid. This would be the form of the amine. So this is the form of the amino acid that would exist. All right, so what makes it interesting is when you have relative pHs that are kind of in between. All right, so at a pH of about 6, all right, notice that such that this would be the predominant form of your amine, but at a pH of 6, this would be the predominant form of your carboxylic acid. So you essentially have the HA form of your amine, but you have the A- form of your carboxylic acid, all right, which would be, you would say that's the carboxylate form, all right. So notice that there is not any pH, all right, where this thing exists as a completely uncharged form, all right. Notice there is no pH where it would exist like this, where this is the NH2 and this is the C double bond 8 or COOH, all right. And that's going to have a pretty significant effect on the way these things behave. All right. So again, there's no pH where the free amino acid would exist chargeless. All right. And what I mean is without any charges on it. All right. And there's a name for this particular type of a molecule right here, and that's called a zwitterion. All right. It's spelled like this, but when you pronounce it, you pronounce the W as a V. It's zwitterion. All right. And what that is a molecule that has at least one positive and one negative charge but it has an overall neutral charge. All right, so notice there's a positive and negative, but it's neutral.